Okay, sweet. I'm going to go ahead and get started. So this is my final project, and I'm going to be focusing on COVID-19 chest X-ray classification, and my name is Cynthia Burke. So some brief background on the problem statement and motivation. Within recent years, X-ray classification has been increasingly popular with studying and research, and there's a bunch of different data sets for this area of research. So what I'm going to be focusing on is chest X-rays that can detect COVID-19, pneumonia, and other chest-related illness. And what I'm trying to do is use better use of the labeled data that is provided within data sets that have labeled data. Since there's a bunch of data sets out there that don't have any labeled data, I feel like it's very important to use it effectively, which is where I'm going to bring in supervised contrastive learning, which is a tool I read a paper on, and it's essentially making more effective use of labeled data within data sets. So, and it also has been shown to improve performance for multi-classification deep learning problems. So the data set I'm going to be using is COVID-19 radiography dataset, and this is based off of Kaggle. And this dataset is consisting of chest X-ray images for COVID-19 positive cases, along with normal and viral pneumonia. And this is the split up here we can see on the slide for all the different numbers of all the different classifications. So there's 4 total classifications: COVID, lung opacity, viral pneumonia, and then normal. And here we can see the differences in all the number of images. So the one with the least amount is viral pneumonia, and the one with the most biggest amount of images is the normal. So we can see here that there's a big difference between the amount per class, which for some classifiers would be an issue with, since there's so many normal images compared to the other ones, which is where we bring in the supervised contrastive learning. And this is going to be a little different compared to normal classification problems. So the first thing we have to do is apply random data augmentation. And this is to essentially showcase the differences between the classes, as well as show the similarities between the classes. And so then there's going to be a different training scheme. And this different training scheme is split up into 2 different stages. The first stage is going to be to train an encoder, which is going to learn to produce vector representation of input images. And the goal here is to essentially train this encoder separately from the classifier. So that way it can learn the differences and similarities between the multi-class problem. And after we pre-train this encoder, we're going to freeze it so the weights will not be updated. And then we're going to train a separate classifier on top of the frozen encoder, which means the only weights being updated in the second step are going to be for the classifier model itself. This fully connected layer, all those layers are going to be weighted, the weights are going to be updated using this frozen encoder. So what my approach is going to be to train 2 different models. The first being just a normal baseline classifier, which I'm going to be using a resonant 50 using cross entropy loss. And then I'm going to have a separate model, which is going to utilize this new approach, supervised contrastive learning, with the 2-step training we saw previously. And so I'm going to train both of these on the same data set for the COVID-19. And then I'm going to compare their sparse categorical accuracies and their area under the curves to see if it is actually going to improve the performance. And if so, where is it getting a lot of them wrong or correct? And to analyze the differences between these 2 approaches. So this supervised contrastive learning also has a new loss function, and I've gotten this from the paper I referenced at the end slide. And so this equation here is this new loss function for supervised contrastive learning, and this is derived from self-supervised learning. The only difference is they actually implemented it so we can handle labeled inputs instead of just self-supervised inputs. So the benefit to using this loss is actually it allows more generalization to all the differences between the positives between classes and the negatives between classes. So there's actually a better contrastive power that increases with more negatives. So this is what I'm going to be utilizing to pre-train the encoder. And then here are my preliminary results. On the left side here, we can see the baseline comparison, which I trained for 50 epochs. And this is the cross entropy loss, which is decreased over 50 epochs. And then this is the sparse categorical accuracy, which increased as training went on. And after training this model, this is just the baseline resonant 50. I got a test accuracy of 77.37%. And on the right here, this graph is showing the classifier that's trained with the frozen encoder weights. So this is me training the supervised contrastive model after pre-training the encoder. And I trained it on the same amount of epochs. And here the losses went down over time, as well as the sparse categorical accuracies went up. And it actually achieved a higher test accuracy than the baseline comparison, which would indicate that using this self-supervised contrastive model, it was actually able to perform better and make better use of the labeled data. And the work that still needs to be done is I want to run this on different backbones to see and verify that this is going to improve with all of them. And then I also want to analyze any differences I see, as well as I still need to implement getting the AUC scores to highlight the comparisons between these different models and see what they're getting correct for classifications and what they are getting incorrect for classifications. And then, does anyone have any questions?